Testing, testing, 1, 2, 3, testing, testing. Am I in frame? There we go. Hello. Good morning, everybody. Hope everybody's doing well today. We are having our last class before the test on Saturday. So I see we have... Oh my goodness. Why? God almighty. Jesus, Mary and Joseph. Ugh. Frickin'... That's what you get for balancing one of those things on a book. That's slightly too narrow for the base of the tripod. All right. Anyway. Shut up, me. There we go. All right. So, how's everybody doing? Maybe I should open the class today with if anybody has any questions, comments, or concerns. Most particularly, if anybody has any questions about the test that's coming up on Saturday. Thank you. This is like my around the house sweater, which you know, sometimes a cardigan just like isn't enough. You know, you have to have a full thing without buttons. But anyway, if anybody has any questions about the test, I would love for us to be able to get that out of the way before we get into our lecture material today. So if anybody has any questions, please feel free to pop those into the chat now. I'll answer the most common questions first. The test coverage is up to the end of this set of lecture slides, so we're going to be reaching the terminus of the test material probably about 15 minutes into our lecture material today. Will A4 content be on the test? I believe so. A4 covers recursion, if I'm remembering correctly, so yes. How can we tell when recursion will be a good strategy? Any cues in the question? Interesting. So, recursion is a good strategy if it results in an answer that's simpler than a answer that you would do using imperative means, roughly speaking. That's like the general case answer to your question. With respect to the test, normally if a recursive answer is expected, that will be obvious. The question will say something about requiring recursion in it. So, you know, if we're expecting a recursive answer, that will be obvious on the test. With respect to cues, to my knowledge, there are no cues on the test. I'm not sure if we're talking about the same thing, but yep. So, will the week 6 video be on the test? Is this the week 6 video? Am I currently doing week 6 videos? I know I'm working on topic 5, and if we're a week behind, that means it's currently week 6. But if it's because of the break, maybe this is week... I don't know. How far behind am I? Jeez. Let's just say everything in the course up to this lecture is testable. So, there you go. Is it going to be the same as last time where you have Alt A to complete it? Yes. The test will be offered in the exact same format as the last test, so you guys should have some degree of familiarity with the procedure. Yep, so the test opens at 9 a.m. on Saturday morning, and it closes at 9 a.m. on Sunday morning. So, yes. I feel like recursion is generally not the best strategy. It takes a whole lot more brain power. I'd be inclined to just use a loop unless I was forced to use recursion. Yeah, it depends. There are definitely problems that are easier when you use recursive solutions for them. However, if you're just sort of learning, like if you're in the category of, this is the first programming experience you're having, is taking this class, definitely I would try for a more straightforward imperative solution before I tried anything fancy. It's kind of like the when you're learning Kung Fu, you got to master the basics before you can do the advanced stuff type thing. Are all the rules the same as the last time? Can you use Piazza? Yes. So Piazza will function in the same manner as it did on the first test. If you have a question for your TA, please put that up in Piazza, and everybody will be monitoring Piazza and answering questions as the day progresses. Oh, the reading week material. Oh yes, what? Yes, that is definitely going to be on the test. For sure, that's going to be on the test. What is the performance typically on test 2 compared to test 1? You mentioned that last time test 1 usually has a high average. Yes. So it's kind of difficult to write a test 1, or to design test 1 such that it doesn't have an average in like typical test 1 averages are somewhere in the 90% range. In this, or even higher than that, if you can imagine that, this particular semester, we had a test 1 average of 80%, which means I don't have to kill you guys quite as hard on test 3. So, because it's, if test 1 wasn't a gimme, that does kind of influence my decision about how hard to make subsequent tests. Like, it's horrible to say, but there is a degree of grade management that goes on in the design of tests. Because it's not good if the entire class has 95%, and it's not good if the entire class has 55%. Hypothetically, you want the class to be a nice little bell curve, and you want the median, you want the sort of middle grade in the class to be like a B-ish. That's sort of that's how grades are supposed to work. So, it's not necessarily a bad thing that the first test wasn't extreme, wasn't, the average on it wasn't 110%. So, generally speaking, yes, there is a drop in the grades as the material becomes more and more difficult. Generally, I'd say there's a lot less of a drop between test 2 and test 3 than there is between test 1 and test 2. So, that being said, there's not as much on test 2 relative to, in different semesters, test 2 would have had more material in it, but just because of the way things worked out this semester, it's going to be a little bit lighter on the new material, which might make it more manageable. So we'll just have to see. My intention is not to kill you guys with it, but we shall see how it goes. Anyway, so all right, I think that's good. Thank you very much for your questions. Let's continue with our lecture material. So, we were talking about the binary search algorithm. Remember? So, very roughly, very quickly, with binary search. Binary search relies on the dataset that you're searching through being ordered. If the dataset is ordered, then we can make decisions about how to search it based on the values in the dataset, right? So if we have a list and it's in order, we can take a look at the middle value in that list, decide what its placement is relative to the element we're looking for if that element exists in the list, right? So for like the numerical example is easiest, but you can actually order strings like this as well. So if we're searching for the value of 33, we look at the value of 22, we know that everything that's sort of left of this 22 in this list, those are all going to be values that are still less than 22. So we can exclude all of those values from our search and focus on a sublist, which is every element that is sort of north of the middle value. You know, the 33 must exist somewhere in that space. We take that procedure and we repeat it on the sublist. So effectively, what we're doing is we are this is like a good mental framework for how this algorithm works. Is you should think of it as search spaces, right? So when you start off, the search space that your element might exist in is the entire list. In the first step, we eliminate half of those from being possible locations for the element we're searching for. We reduce the size of the search space by half at each step. At each step, so as we continue down through that, we are, roughly speaking, guaranteed to have either found the element or not by the time that search space is reduced to 1. And the number of steps it takes to bisect the list until you hit 1 is log base 2 of the number of elements in the list. So that means that the runtime of this algorithm is proportional to the base 2 logarithm of the size of the input array. And that's really good. If exponential growth in your runtime is the worst possible case, if that's the worst possible runtime behavior, and linear is really good, then logarithmic is like super fantastic. Every algorithm wants to be a logarithmic time algorithm. Because that means, to go from being able to deal with 1 million to 2 million inputs, all you have to do in that case is add one more step to your algorithm, right? You can double the size of the number of things you can deal with anyway, you get the idea. Anyway, we did this last class, so this is the implementation. Fine, cool. Binary search using recursion is much faster because it only has to look at a small number of items in the list. If the list has a length of n, then binary search using recursion looks at approximately log base 2 n elements of the list. So the question then, this sort of begs the question, okay, but, what if my list isn't in order? I can't use this algorithm, right? And the answer to that is yes. Unless the list is in order, you can't use the algorithm. And putting the list in order, that takes time, right? That's what we call a sorting algorithm. And sorting algorithms are they're like a very venerable field in, a long venerated field in algorithms research, sorting algorithms. In fact, it's been in existence since the 1950s, and we're still making discoveries about ways to more efficiently sort the items in a list. There was, I believe it was 2006, there was a new sorting algorithm that was developed that was better in some cases than all of the existing ones. But you've got tons and tons of different sorting algorithms. You've got sort of bubble sort, which is your most basic sorting algorithm. You've got insertion sort. You've got shell sort. You've got quick sort. You've got library sort. You've got is it Jake Sort or Jack Sort? And some guy named it after himself. But that's, totally fair because shell sort is actually also named after a person. It doesn't have to do with shells. That was the person's name. So, yeah. But we're not really going to get into sorting algorithms. For those of you who are going to take more computer science courses, when you take DM3, 1DM3, which is your first year data structures and algorithms course, it is likely you will get a reasonably thorough treatment of sorting algorithms. So, the version on the previous slide is still somewhat inefficient because it creates a new list every time by slicing. The next slide shows binary search using recursion by keeping track of start and end points of the sublist rather than making a new list each time. So that's the thing. Again, when you perform slicing operations, you always have to keep in mind that every slice you perform is allocating new memory for the new sliced list. While this isn't, it turns out that when you do binary search via list slicing, you'll never allocate more than the size of the original list in slices because, it's kind of like Zeno's paradox. It's like, or not Zeno's paradox. It's like whatever that sequence is, but it's like 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 all eventually adds up to 1 if you take that list going to infinity, right? Math has applications. So, the alternative way of doing this is to just keep track of where the endpoints are and move the indexes. This is far more memory efficient because you don't have to sort of duplicate the list and take up all that memory for every time you want to, compute a sublist. You just move, kind of similar to how the Newton's method example for way back from slide set 1. If you guys remember the first example we did in this class, the Newton's method example, in the same way that one is taking like the A and B bound and just sort of moving it in. You can do the same thing with this list searching, but I won't go into it in super degree of detail. So, there is one interesting thing syntactically about this that you might be interested in, though. Did you know that you can define a function within a function? That's right, folks. You can define what are called, usually called helper functions. So, if you define a function within a function, that function is local to the function in which it has been declared. So, search3 helper does not exist outside of search3. It's local to that function. And you might be like, well, why would we ever need to do that? And the answer is, well, you probably don't. It's just, it's a way of constraining the domain of your functions that you're writing so that, if you write a function that's meant for one particular use and it's only applicable within the context of some other function, that that makes it a good candidate for being placed inside of that function. Because, if it's not necessary to any other function, then why make it available to any other function? It's sort of implementing, once again, the principle of least privilege. So, there we go. I'm just going to check to see if we have any questions. Poor Zeno. Why won't math give him a break? Yeah, that is Zeno's paradox, yeah. Is binary search currently the most efficient algorithm people have come up with for searching? I don't want to say yes, because it's entirely, like, I'm not an expert. Like, you'd have to be an expert in algorithms research to be able to answer that question, and I'm not, so. Should you be practicing sorting functions? Well, it's definitely a it's definitely, like, if you're looking for good practice material, implementing some sorting functions, that definitely, that's the good stuff, for sure. Isn't there a built-in function to sort a list? Yes, but the question is, what algorithm does it use? Right? It's like, just because you have a function available doesn't mean that it's just the function name. Although it's useful to be able to abstract it like that, you sort of have to do this interesting double think, where it's like, yes, I don't have to worry about anything about the sorting function, it just sorts. I don't have to worry about how it does it, but at the same time you have to think, at least when you're in this class, you have to think, okay, sure, but is the algorithm that it's using an efficient algorithm? And yes, in the case of Python, it is a pretty good... It's one of the recent sorting algorithms that they use. I believe it's JakeSort, or whatever that guy's name is. Yes, Lambda functions, that's actually something we're about to talk about, I believe. Yes. So, functions as objects. So, Python is an object-oriented language. In Python, functions are first-class objects. So I can demonstrate. Let's say we define a quick little function, add xy, returns the value, return x plus y, bing bang boom, just to demonstrate, not dad, there we go. There we go, add function. Type of add, class function. So we're going to get into this when we get into object-oriented, but when you define something, when something says it's a class, that means that classes are the basic constructs of object-oriented programming. Very roughly, when a class is like a template that incorporates both data and procedures, and an object is an instantiation of that class. So when it's like the difference between declaring a function and using a function. When you use the function, that's the same as using the class, which makes it an object if it's a class, whereas you can define the class separately from it being used. But don't worry about that too much yet. We'll go over that in great detail when we talk about object-oriented programming. So the important point is that functions are objects, which means we can manipulate them similarly to how we manipulate other things, right? So for those of you who have used Haskell to any degree, this will be very familiar to you. But in Python, you can pass functions as arguments to functions. All right? So, yeah. So let me give you an example. Let's say we had a list. 1, 2, 3, 4, 5. And let's say we wanted to add 7 to every element of this list. We define a function, add 7, takes argument x, return x plus 7. Now we have a function. It adds 7. How do we apply this this function to every element of this list quickly and easily? You define a mapping function. Mapping functions are something that are very commonly used in functional programming settings. And they're also useful in non-functional environments as well, but, you know, people typically just do it with a loop rather than with a function. So, define map. Takes a function f and a list lowercase l. I is equal to 0. I'm going to do it with the while loop, because why not? While I is less than the length of little l, L at I is equal to F at L at I plus equals 1. Return L. There we go. So, if we print a map of the add7 function over the list L, capital L, there you go. What it's doing, so what's happening here is this F here, when it's provided a function name, you can use it inside of this function like a function. See how it's being used in function syntax? So, you know, one of the disadvantages of doing this in Python as opposed to Haskell is when you do this in Haskell, the number of parameters and the types of the parameters that you're using have to be reasonably rigidly defined, which makes it easier, actually, as opposed to Python. Like, if I put in a function here, like regular add, that takes 2 arguments, I would run into a type error because it's missing a positional argument when it's being called here. So, you know, somewhere in your documentation, it should say that this guy takes 1 argument. But, you know, it's kind of neither here nor there. But anyway, yeah, so that's an example of being able to pass a function into a function as a parameter of that function. Everything's getting very meta all of a sudden. Let me see, have I lost everybody? Oh, is that a funny face? Am I on a funny face again? It's not as funny as it could be. There we go. And whenever it does that, it also switches my my microphone. Okay. Right. Cool. Testing, testing. There we go. You don't understand the purpose of this. So, why is this useful? Well, let me ask you a question. Okay. Doing a function in this manner allows us to abstract the actual procedure that we are performing on the list. So it doesn't matter if we, like we could define another function, say like mult3. All that does will multiply the value by 3, right? And then we can perform this map on, you know, mult3, rather than... We can map this multiplication over the list. We don't have to write a new map function, right? Same map function, different functionality. It's like... What it does is it elevates functions to the level of, like, modules that can swap in and out of different other procedures. This won't seem like it's very useful, but once you start getting into, like, real heavy, hardcore, you know, data manipulation, this stuff is going to seem super useful. In particular, if you are going to be doing like a minor in computer science, and at some point you're going to do 1JC3, which is the the course on Haskell programming, this is the type of mind that you need to get into to do Haskell programming, or functional programming in general. Like, you should think of functions as an abstract unit of data. Procedures can be swapped in and out in the same way that you can data. It's actually extremely useful to be able to do this. But yeah, I don't know. Like, for a beginner level stuff, yeah, it's like this is on the slide so that it can be, you know, so that it can be in the exam type thing. Cool. All right. So, here is the precise example that I just did, except in this case they're using math.cosine instead of like a custom defined thing. So yeah, you know, sure, you can do math.whatever, you can do square root, any function. That's the point. So, the other thing that we can do is we can do what are called anonymous functions, and this is where Haley was asking for lambdas. This is what a lambda is, even though you know, in Python, like, people use the word lambda, but they don't really know what it means. Lambda means function extraction. It's like function extraction operator. So if I have an expression, let's say I have an expression like x plus 3 times y, right? That's just an expression. If x and y don't exist, then, you know, they don't have concrete values, and we can't compute the expression. However, if I designate lambda x comma y, colon, and then the expression, what this does is it turns the whole gosh darned thing into a function. So, this is a way of declaring functions in line without having to give them proper names. Again, if you're programming in Haskell, this is your bread and butter. So, it's a way of turning an expression into a function by designating which symbols within the expression you want to make into arguments. So with a lambda, you can actually you can provide it arguments. Oh, geez, there we go. You can provide it arguments just like you would provide a regular function, and it just works, right? If you don't give it enough, it'll complain at you. It's missing a positional argument. So this is a way of declaring. Again, it's really just declaring a function, but you do it in one line, and it's usually just an expression. Like, you know, one might say, this is overkill. Defining like mult3, that's overkill for what it's doing, and it's just cluttering up your, it's cluttering up your program with functions that don't need to be necessarily declared functions with names, right? So you can just as easily print map lambda x plus or multiplied by 3 and then provide it the list L, and then it just works. So yeah. So anyway, that's all that we have to talk about with functions. So, yeah, any questions about any of that? How are the variables given to the lambda function syntactically? That's a good question. So, so take this line as an example, right? If you remove this bit and replaced it with a function name, it's exactly the same as how you would call a regular function. So you can think of this expression, this lambda expression, as being directly substituted in the code for a function name, and then everything else is exactly how you would normally use a function. So there you go. 1JC3 was the first comp sci course I ever took last semester. It was very tricky. Yup. Yup. Tricky doesn't even begin to describe it for a lot of people. Okay, so, good. In that case, I think we shall, go on to topic 6. We got 15 minutes left in class. Avenue. God, get out of here, Opera. You were too slow. All right. There. So, having spoken at length about functions and all of that stuff, now what we're going to do is we're going to do a bit of a deep dive into data types, how those data types are stored in terms of actual computer memory, and some of the pitfalls that exist with respect to the underlying digital representations of numbers. This is numerical computations, topic 6. Let me just see if we have any questions. Topic 6 is not on the test, no. That would just be cruel. So, integers. So you think you know how integers are stored? Ha! Well, so in base 10 arithmetic, which is, normal Arabic numerals, we have each place value in a number, sort of, you multiply by increasing powers of 10 to arrive at the final result, right? That's how numbers are composed. I know this seems somewhat facile, but there is a point to this. So, like, the thing in the thousandths place is multiplied by 1,000, which is 10 to the 3. Notice the progression of the exponents here. That's very important. In binary, it's the exact same bloody thing, except the base is 2, not 10. Decimal system base 10, binary system base 2. This is how numbers work. So, in binary, we've got 2 to the 0, which is 1, 2 to the 1, which is 2, 2 to the 2, which is 4, and 2 to the 3, which is 8. So the binary number 1101 is 8 plus 4 plus 1, which is, of course, 13 in base 10, right? I'm going to skip the quiz. So, in order to convert from binary into decimal, the rough approach that you have to take is to compute the sum in terms of the relative powers of 2, right? So, as we did on this slide, you write out the expression with all of the multiplicative factors in there, and then you perform the summation, and that's how it works. Easy peasy. In Python, you have to be a little bit careful because, you know, you always have to keep in mind that indexing starts at 0 in Python. So in Python, the way that binary numbers are represented is actually with strings, which is super stupid, but that's how they do it. So if you want to convert to an integer, how does it work again? Is it decimal? No? Can I convert it to a hexadecimal at least? Does that work? Yes, okay. So if you want to write a binary number in binary, you must preface the binary number with 0b. That will allow you to enter something into the computer in binary notation. Similarly, if you want hexadecimal, you use OX. That's a hexadecimal number. And we won't talk about octal, because nobody ever uses octal. But if you wanted to, it's 0O. So, yes. Let me just see. So, if we wished to write a Python function which converted from binary to decimal, it's reasonably straightforward. If b is a string of ones and zeros, then we declare d with we start a sum variable d, which will be d for decimal, for every element in the list. If b at I is equal to 1, then d plus equals 2 to the power of the length of b minus 1 minus I. So that is to say, 2 to the power of however many digits there are, subtract 1, because of course we're indexing is from 0, subtract the 1, however far along we are in the list, because we start at n minus 1, then n minus 2, etc., all the way down on to 0. So, you also have the ability to do what's called Horner's rule. Horner's rule is basically, if you take a look at the way that this is done, you don't actually have to ever at any point invoke exponentiation. You can just continually multiply by 10 at each step, right? It's kind of like, in decimal, you can kind of imagine it like, add the least digit, move it up, add the least digit, move it up, add the least digit, move it up. That's kind of the procedure that they're talking about here. So you can also do this according to Horner's rule, but, yeah, you can see it's like, this is the equivalent of move it up and add the least digit. Move it up, add the least digit. Takes fewer lines of code, because we're relying, in this one, we're kind of relying on an if statement to determine whether a digit is 1 or not. In this case, we're just sort of converting directly to an integer. If it's 0, then whatever, and if it's 1, then also, it'll just interpret it correctly. So, let me see. So, going the other way, that's a little bit more tricky. So if we have a decimal number and we want to convert it to binary, what we have to do is we have to perform subsequent modulus and division operations. And that kind of makes sense, right? If we're building it up, then we use multiplication. If we're tearing it down, we're using division, right? Nice symmetry there. So let's imagine we had a number like 8,572, right? Whether or not the least significant digit is a 1 or a 2 is actually the result of 8572 modulo 2, right? So it's 0, so our first binary digit is 0. We then shift the whole thing down by that place value, which is integer division by the value that we're whatever the base is for the system what we're converting to. Incidentally, this procedure works for all base systems. Base 10, base 2, base 8, base 16, base 17, base 3272, whatever base you want, this works for it. So, 4286 modulo 2, that's also 0, so the next least significant bit will be 0 as well. We then divide by 2 again. 2143 modulo 2 is 1. So our binary is now 0, 0, 1. We divide by 2 again. We get that. Modulo that. So we got 0, 0, 1, 1. Divide by 2 again. 535 modulo 2 is 1. 535 divided by 2 is 267. 267 modulo 2 is 1. Divide by 2 is 133. So right now our binary number is 0, 0. Oh, I should reverse for you guys. 0, 0, 1, 1, 1, 1. 133 modulo 2 is 1. Divide by 2, 66. 66. I know that its modulo is going to be... You can, with modulo 2, you can just tell by looking at it if you're a human, but, we'll just follow the algorithm. Sorry. 66. So 33 modulo 2. There we go. Anyway, you guys probably get the point. You take all of these binary digits, you compose them into one number, and that's the reverse algorithm. Questions? Nope. Okay. So, gonna skip the questions. Yes. Oh, actually, this is an important point. When you're dealing with binary digits, in the same way that you deal with like regular decimal digits, in decimal, they're like 0000584 is like you just drop the leading zeros, right? And that's your decimal representation. In binary, you kind of drop the leading zeros as well. So that, like, 00001111 is the same thing as 1111. The thing is, normally with binary numbers, you're like concerned with how many bits you're representing, right? It's like, I need an 8-bit number, so you're sort of naturally inclined to include the 8 bits, whether or not they're, like zeros at the front that don't actually affect anything. So, you can enter them, but they don't have an effect on the value, just like leading zeros on a decimal number don't have an effect on the value. So, here is an encoding of the decimal to binary algorithm, which I just showed you guys. So, yep. To clarify, this method is moving from integers to binary. I want to refine that way of thinking about it a little bit, because these binary numbers that we are describing here are also integers. In fact, they are definitionally integers. This is how integers are represented in your computer system, right? The difference is we are moving from base 10 integers to base 2 integers. We are going from decimal integers to binary integers. So, because, whether or not something is an integer, the properties of integers do not intersect with the base in which they are represented, right? So in order to kind of get this, you have to separate in your brain the base in which a number is represented from the properties of that number, which is something we're going to see even more once we get into floating point notation. But yeah, that looks like time. If there are any other questions, I'd be happy to answer those now. Please keep in mind that I'm having office hours immediately after this class ends and as soon as I make myself a cup of tea. So if you have any longer questions, you're absolutely welcome to join me in the office hours. But yeah, cool. Any questions? Okay. And looks like everybody's cool with everything, so I guess I'll sign off here. Good luck on the test, everybody, and if you have any questions, again, office hours immediately after I make myself a cup of tea. So, take her easy, folks. Keep it cool. Everything's cool. Be cool.